Hey everybody, welcome to our second narrated PowerPoint. Hopefully everybody is staying home, staying healthy, and doing well. But today we have another PowerPoint with some new physics to go over. So in the last PowerPoint with electric current, we started talking about some simple circuits and some of the basics of circuits. But in this one, we're going to start looking at more complex circuits, namely series and parallel circuits, where things get a little more complicated, and we have some new rules that we're going to have to follow and some new math we're going to have to be able to do. Okay, so I sort of gave this away on the first slide, but there are two types of electrical circuits we're going to be looking at. First are series circuits. So you can see here from this picture how these two light bulbs are in one series or in one line, which means they're going to be, our electric current is just going to follow one path through both light bulbs. And the other type of circuit is a parallel circuit, as you can see in this picture on the right. And you can see in this case, there are two parallel paths that the current could flow through. So we're going to be looking at both of these in a lot more detail, but these are going to be the two basic types of circuits we're going to be looking at. Series, where things are in a single line and there's one flow of current, and parallel circuits, where there are two different paths that the current can go through. Alright, so first we're going to take a quick look at series circuits. So you can see here the same pictures we had in the last slide, as well as a circuit diagram of what this circuit would look like. And so for a series circuit, the components are connected end to end, one after the other, creating a simple loop for the current to flow around. Right? This is just the current flowing through this circuit is just going to follow one path all the way through. It's going to pass through both light bulbs and then go back to the other terminal. And for a series circuit, if one bulb blows, it breaks the entire circuit, right? If you have an issue with one of these light bulbs, now you don't have a complete circuit anymore, and you're going to have no current flowing anymore. Alright, here we can see our picture of a parallel circuit, this time with a circuit diagram of how you would draw that out. And so parallel circuits are different in that the components are connected side by side instead of along the same path. This makes it so that the current has a choice of different routes that it can take from one terminal of the battery to the other, which means that if one bulb blows, there's still going to be a complete circuit to the other bulb, so it's going to stay alight. So even if this lower light bulb completely breaks, goes out, right, which would normally, like in a series circuit, break the circuit, in this case you would still have a path from positive through the other light bulb to the negative, so you would still have current flowing, and this top light bulb is still going to be lit up. Alright, so if we want to measure the current in a circuit, if you guys remember from the last PowerPoint, the unit we're going to be using is amps or amperes. So we use something called an ammeter, like this picture on the left here, and we connect it in series with the circuit to measure the current. Alright, so on this slide here we can see how we actually draw an ammeter in a circuit diagram. So on the left we can see a picture of a series circuit, and you can see that the ammeter is just placed in series with both of our light bulbs, right, and the same current is going to be flowing through all three. The ammeter and both the light bulbs are all going to have the same current flowing through them. For the parallel circuit here on the right, you place the ammeter after the two routes have reconnected, so you get all the current, because right, we know now there's two routes the current can flow through, so the current's actually going to be split between these two light bulbs. So you place the ammeter in series with both of them up here after the routes converge. Alright, so to talk a little bit more about why we were putting the ammeter where we did in that last slide, we need to look at what the current looks like throughout each of these circuits, series and parallel. So in a series circuit, the current is going to be the same at all points in the circuit. Right, since there's only one path for current to follow, you're just going to have that same current anywhere throughout the circuit. So wherever you put your ammeter, you're going to measure the same current. So in this picture here on the right, there are 2 amps of current flowing through this circuit. For a parallel circuit, on the other hand, the current is shared between the components. Right, so now that there's 2 paths to follow, that current is going to be split between the two. So at the beginning and end, when there's only one path, we have 2 amps of current, but where it's split into 2 paths, on this circuit here, we have 1 amp of current going through each of those paths. Right, so originally we have 2 amps, it splits into 2 paths with 1 amp each, and then they reconverge, and you get back to 2 amps of current. Alright, and something else we might want to measure in our circuits is the voltage. So voltage is basically the electrical push that causes the current, right? So that'll be from our battery, from our power source, from whatever we're using, right? The voltage or the potential difference is just what's causing the charge in the wire to move and move that current. So we measure voltage in volts, and in a circuit we use a voltmeter to measure that. So all pretty easy to remember, right? Voltage measured in volts, you use a voltmeter. All the names are pretty much the same thing. And then here we see a picture of what a voltmeter might look like and how we would draw a voltmeter in a circuit diagram. Right, so basically you just draw a circle sort of in your circuit, put a V in it, and we know that that's a voltmeter. Alright, so and when we talk about measuring voltage, the first thing we need to know is that different cells produce different voltages. Right, so depending on what battery or what power source you're using, you're going to have a different voltage applied to your circuit. And that the bigger that voltage is, the bigger the current is going to be. Second, unlike an ammeter, which is connected in series, a voltmeter is connected across the components. So that's going to be a little easier to think about on the next slide, because we're going to see what that looks like in a circuit diagram. The voltmeter is always connected across the components that you're measuring the voltage of. And then finally, scientists usually use the term potential difference when they talk about voltage. Right, so potential difference and voltage mean the same thing. Right, there's just two different ways to talk about the same concept. Alright, so now on the last slide we're talking about measuring voltage, and I mentioned that you draw a voltmeter across components. So now we're actually going to look at what that looks like in a circuit diagram. So if we see here for the series circuit on the left, we draw this voltmeter in parallel to one of the light bulbs, and that would give us the voltage going across that light bulb, or the potential difference across that light bulb. On the parallel circuit, basically you do the same thing, right? You just connect it going across, or basically in a parallel circuit with one of the light bulbs. And that's going to give you the voltage going through that light bulb. Alright, now we're going to look at what the voltage would look like throughout a series circuit. So for series circuits, voltage is shared between the components. So we can see here the voltage of the battery is 3 volts, which means through these two identical light bulbs we have 1.5 volts through each of them. Right, so the total voltage is going to be shared between the components that we attach to this circuit. Now in parallel circuits, on the other hand, the voltage is going to be the same in all parts of the circuit. So right, in this case, the battery, or the battery cell here, is 3 volts, same as before, but because these two light bulbs are in parallel, we have 3 volts going across both of these light bulbs. Right, so whether you wire them in series or parallel is going to have a pretty big difference on the voltage going through them, and if you remember from earlier, also on the current going through each one. Alright, so we've looked at current and we've looked at voltage in more complex circuits, so series and parallel circuits, and now we're going to start looking at resistance. So first, when you put two more resistors connected end to end, they're said to be in series. Right, so like in the circuits we've been looking at, the light bulbs would be resistors. So we're just talking about what's going to happen when we put them in series. And so we know in a series circuit, the current is the same through everything. So the current would be the same through all the resistors, because any charge that flows through one flows through the others. There's only one path the current can follow. And the sum of the potential differences across the resistors is equal to the potential difference across the combination. Right, so if you have two resistors, you could add the potential difference across both of them together to get the total voltage of the circuit. Alright, so I just mentioned that for resistors in series, the potentials are going to add. So here's sort of some of the math of what that's going to look like. So if we have a delta V from this battery, we know that's going to be equal to IR1, which is the voltage going through this resistor on the left, plus IR2, which is going to be the voltage flowing through this resistor on the right. And these two pieces we just got from Ohm's law, which is from our last PowerPoint, V equals IR. So the voltage across R1 is equal to the current, which is going to be the same for all of these, times R1, or the resistance. Right, same thing for R2, we know V is equal to IR2. So the total voltage supplied by the battery is going to be split between these two, which is going to be IR1 plus IR2. And then if we just factor out the I, because we know the current is the same for both of these, we can get that delta V is equal to I times R1 plus R2 in parentheses. And that's sort of what this formula here is telling us. And this is basically a consequence of conservation of energy, right? However much voltage is being supplied by this battery here is how much can be used between both of these resistors, right? So the total voltage from the battery has to be equal to the voltage used by the resistors. And then if we look at our sort of third form of this formula, the I times parentheses R1 plus R2, we can start talking about something called equivalent resistance. So the equivalent resistance has the effect on the circuit as the original combination of resistors. What this means is we know what effect is on the circuit with these two resistors here. If you took these out and you replaced them with one resistor with the equivalent resistance, which would be R1 plus R2, you'd have basically the same circuit. So the circuit would have all the same effects on it. Alright, so to talk a little bit more about equivalent resistance, for a series circuit, R equivalent is going to be equal to R1 plus R2 plus R3 plus however many resistors you have. And this equivalent resistance is a series combination of resistors, is the algebraic sum of the individual resistances, and is always going to be greater than any of the individual resistors. Right, so as you add more resistors in series, you increase the equivalent resistance, right, because the total sum of the resistors is going to go up. Right, so remember, for resistors in series, this is how you find the equivalent resistance. Alright, to give you guys an example of sort of how we use equivalent resistance, we have this circuit A on the left here, which has 4 resistors of 2 ohms, 4 ohms, 5 ohms, and 7 ohms. And because we know the equivalent resistance is just going to be the sum of those 4 numbers, you can actually also draw this circuit as we do here at part B, where you just replace all 4 of those with a single 18 ohm resistor. So you can replace those 4 resistors with one equivalent resistor, and the circuit's still going to have the same current, same voltage, and all that. Right? These two circuits are basically equivalent. Alright, so we talked about finding the equivalent resistance of resistors in series, but now we're going to look at parallel circuits and resistors in parallel circuits. So just to remember some of the differences between series and parallel circuits, for a parallel circuit, the potential difference across each resistor is going to be the same because they're all connected directly across the battery terminals. Right, so if you remember from those slides that we looked at, for a parallel circuit, the voltage across a given component is always going to be the same when they're in parallel. For the current, on the other hand, because the current that enters a point must be equal to the total current leaving that point, the current's going to split. So you'll have a total current I that gets split into I1 plus I2 if you split into 2 parallel paths. And this is a consequence of conservation of charge. Basically, if you only have so much current, and it has to go through 2 paths, it has to be split up between the 2. So because this is different from how a series circuit works, finding the equivalent resistances of parallel circuits is going to be different as well. Alright, so when you want to find the equivalent resistance of a parallel circuit, or resistors in parallel, this is the equation you're going to use. So 1 over R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3 plus so on, however many resistors you have. So basically what that is that the inverse of the equivalent resistance of 2 or more resistors in parallel is the sum of the inverses of the individual resistance. Right? 1 over the equivalent resistance is equal to the sum of 1 over each of the individual resistances. And mathematically, this ends up meaning that the equivalent is always less than the smallest resistor in the group. So if you look at this circuit here on the right, we have 3 resistors in parallel. One is 3 ohms, the second one is 6 ohms, and the third one is 9 ohms. So we know that the equivalent resistance should be less than the smallest, so it should be less than 3. And when I did the math out, I got that the equivalent resistance is about 1.6 ohms. So that does check out. It's less than any of our resistors. So to give you guys an idea of what equivalent resistances are going to look like in circuit diagrams for a parallel circuit, here on the left we have a parallel circuit with two resistors, R1 and R2, and you can see that we can just replace them with a single equivalent resistor. Right, so that's the same as we did for the series circuit, except now we're using a different formula. In this case, we're going to use R1 over R equivalent is equal to 1 over R1 plus 1 over R2. But same as we did before, you can take these two resistors and replace them with one equivalent resistance resistor. And some interesting information is that household circuits are wired with devices connected in parallel. That way, if you have an issue with one, you don't break the circuit for everything and lose power to your whole house. With the exception being circuit breakers, which are usually used in series because we specifically do want those to break the circuit, stop current from flowing just for safety reasons. Alright, so as we start looking at more complex circuits, you're going to see things like this part A here at the top of this page, where you have a combination of series and parallel, and you're going to have to try to reduce that down to one equivalent resistance. So all you have to do is just do that piece by piece and step by step. So if we look at part A, we have these two resistors in series, 8 ohms and 4 ohms, and we know that for series circuits, the equivalent is just going to be the sum of those resistances. So we can combine those into one resistor of 12 ohms. On the right hand side of this circuit, we have a 6 ohm resistor and a 3 ohm resistor in parallel. And we know if we want to replace that with an equivalent resistor, we need to use 1 over R equivalent is equal to 1 over 3 ohms plus 1 over 6 ohms, which would give us an equivalent resistance of 2 ohms. So then from part A to part B, we can reduce down those 4 resistors into 2, a 12 ohm resistor and a 2 ohm resistor. And then these two are in series, so we know our final equivalent resistance is just going to be the sum of those, or 14 ohms. Alright, so one of the last things I'm going to talk about are ground wires. So electrical equipment manufacturers use electrical cords that have a third wire, which is our ground. And so we talked a lot about the concept of ground when we were learning about electric current, when we were using the Van de Graaff machine. And basically, if you have a wire going to ground, you have somewhere you can just dump excess charge with no real issues. And this helps prevent shocks, right? So if you're able to put excess charge into the ground, that stops you from building it up on yourself, so you're a lot less likely to get shocked. So besides just ground wires, there are also special power outlets called ground fault interrupts that we use to help keep us safe. So these are things that are used in hazardous areas that are designed to protect people from electrical shock. And what they do is they sense if there are currents of about 5 milliamps or more leaking into the ground. And what that tells you is that you're building up excess charge somewhere that's causing that current to flow, and then it shuts off the current whenever the current gets up to this level. So basically, if it's noticing that there's a lot of charge going to the ground, that means probably that charge is going somewhere besides where it was supposed to, so it shuts off the current to help keep people safe. Alright, and so before we finish up here, I just want to look back at these two formulas that we got in this PowerPoint. Basically, these are the two new formulas that we have, and it's for the equivalent resistance in series circuits and the equivalent resistance in parallel circuits. So if you remember, for a series circuit, the equivalent resistance is equal to the sum of all the individual resistances, or R equivalent is equal to R1 plus R2 plus R3, and so on. For a parallel circuit, the equivalent resistance, the inverse of the equivalent resistance is equal to the sum of the inverses of the individual resistances. So 1 over R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3, and so on. So these are sort of the only two new formulas that we have for parallel and series circuits, but we're going to be using these to look at complex circuits and finding equivalent resistances. So these are two formulas you're going to have to be familiar with and ready to use for the homeworks and for whenever our test comes up.